let's run through an action potential as it's coming down an axon to a synapse. So now I want you to be thinking about not just an action potential, but what happens as it gets to a synapse. So if we were looking at this particular end of an axon, we'd have an action potential coming down it. And at the leading edge of that action potential, remember we'd have voltage-gated sodium channels that are allowing sodium in, and that plus charge would be repelled away. So as it spreads down here at the synapse, there are voltage-gated calcium channels, voltage-gated calcium. Voltage-gated calcium channels, and that positive charge near the base would pop those open, and we get calcium in. We're going to come back to that calcium because that's very important for what's going on in a synapse. So that's the leading edge of an action potential, and as that action potential is moving along, you'd have voltage-gated sodium channels that are open. That sodium in an action potential, until it gets to the end of that axon, would also be opening more voltage-gated sodium channels. So here's another voltage-gated sodium channel, sodium coming in. And the action potential would be ending down here, okay, where you stop having voltage-gated sodium channels and voltage-gated potassium channels expressed. But at the end of that action potential, sodium would be coming in. Okay, so this is the first half of the action potential. We're at, before the action potential, we're at something like minus 70. Where these gates are opening, we're at minus 45. Where voltage-gated sodium channels are all open, we're at plus 30. Behind that, of course, we'd have the delayed opening of voltage-gated potassium channels, and potassium would be leaving. Okay, so remember the action potential is going this way. So this has happened, and then as that progresses, these will close. So these would be closing, and voltage-gated potassium channels would be opening, potassium would be leaving, and it would continue leaving until we were at minus 80 millivolts. Further back behind that, we'd have voltage-gated potassium channels are closed, and of course all of our voltage-gated sodium channels would have their inactivation gates closed. And so behind here we'd have the only channels open are the potassium leak channels, and we'd have sodium coming in along with glucose or amino acids. Okay, so that would be for an action potential going this way. To finish this off with the events of a synapse, calcium would bind to some calcium binding protein. That calcium binding protein would interact with a vesicle of neurotransmitter. That interaction would cause that vesicle to fuse with the membrane and release neurotransmitter. The neurotransmitter would bind to neurotransmitter receptors on the next cell, and then either the neurotransmitter receptor is an ion channel, and if it is an ion channel, that will allow sodium in. That would be an ionotropic receptor. Remember, the other possibility is that it's a metabotropic receptor, and a metabotropic receptor sitting here and has a binding pocket for neurotransmitter here. A metabotropic receptor would be activating a second messenger. And that second messenger would in turn bind to and open channels in some way. And if this is a sodium channel, if that's a sodium channel, you get sodium in. So in both cases, an ionotropic receptor, you get positive charge in, which can start a new AP, a new action potential, if there's enough coming in, or with a metabotropic receptor, you have ion channels opening, bringing in sodium, and again, if there's enough, a new action potential in the next cell.